This is the section on linear transformations. If x goes to t of x is called the what of x?
Not the transformation.
X going to t of x, so this, right, is the transformation, but t of x itself is called the image. Okay, so there's two things that makes a transformation linear. What are they? What can be switched? You're right. I'm going to write it out here. The order, no. All right, I'll give you a hint. T of u plus v and T of c times u. What does T of u plus v have to equal? T of u plus T of v. Yeah. This one has to be, yeah, C times T of u. So that's what makes a transformation linear. It has to be that you can do, that addition can be done before or after the transformation. Multiplication by a scalar can be done before or after the transformation. And we'll do some examples to help you see what that means a little more. Okay. All right, if t goes from Rn to Rm, what is Rn called? Domain, good. Okay, so today we're going to learn about linear transformations, and we're going to see that multiplication by a matrix A takes a vector x and transforms it into a new vector b. Okay, so we're starting with a matrix A that's 2 by 3, and we're defining a transformation T that takes x to A times x. So in our traditional notation, so this is sort of how the notation you're more used to, T of x equals A times x. So your input is some vector x, your output is A times x. So is T a linear transformation?
How do we know? Is T defined?
T is the matrix that multiplies any vector times this matrix A.
Yeah, yeah, absolutely.
Yes, it's linear. Any matrix transformation is always linear, but let's verify it in this case. Any matrix transformation is linear. Okay, so I'm just going to go to another slide. You don't have to write this down if you don't want to, but I just want to show you that it's linear. So 1, 0, 2, 4, 0, 0. 1, 0, 2, 4, 0, 0. All right, that's my matrix A. And I need to show that A times a vector times the sum of two vectors is the same thing as doing A times the first one plus A times the second one. So what kind of vector does the size have to be in order to be able to multiply A by it? 3 by 1. Yeah, because it's got, this matrix has 3 columns. So if I'm going to multiply by a vector, it needs to have 3 entries. Right. All right, so somebody give me a random 3-entry vector. 2, 7, 4. Okay, somebody give me another random 3-entry vector.
1, 1, 1.
1, 1, 1. Okay, good. All right, so u plus v, if I add those together, what do I get? 3, 8, 5. Good, okay. So I'm going to do my matrix multiplication A times the sum and see what I get. And then I'm going to do it separately, A times U plus A times V. I want to show that they're the same. So NTS is the math notation for need to show. Okay. So I need to show that A, which was 1, 0, 2, 4, 1, 0, 2, 4, 0, 0, times the sum, 3, 8, 5, is the same as the matrix 1, 0, 2, 4, 0, 0 times the first one, 2, 7, 4, plus 1, 0, 2, 4, 0, 0, I'm out of room, times 1, 1, 1. Okay, so I need to show that those two sides of the equation are the same. Okay, that's what makes a transformation linear. You can do you can add first and then multiply, or you can multiply first and then add. All right, so how do I multiply this matrix times this vector?
Yeah, 3 times 1, 0.
Okay, so yeah, each of your 3 columns takes each of your 3 entries in the vector as a weight. So I'm going to have 3 as my first weight times my first column. 8 is the next weight times the second column. And 5 as my third weight times the third column. Okay, so that's going to come out to 3 plus 16 plus 0 is 19. And then 0 plus 32 plus 0 is 32. All right, so that's my left-hand side. I did the addition first and then multiplying by the matrix. And then does that equal the same thing on this side? So I have to do 2 matrix multiplications in this case. Now my weights are 2, 7, 4. Put those on each column. So I'm going to have 2 times 1, 0, plus 7 times 2, 4, plus 4 times 0, 0. And then I do the same thing here, put a 1 weight on each of my columns. So I'm just going to have 1, 0, plus 2, 4, plus 0, 0. All right, so my first entry is going to be 2 plus 14 plus 0 plus 1 plus 2 plus 0. So you get 2 plus 14 is 16, 17, 18, 19. Right? And then my second entry is going to be 0 plus 28, which is 28, plus 0 plus 0 plus 4 is 32. Check. Okay. So we showed that we preserve addition. Right? So addition is preserved under the transformation. And then we also have to show it with multiplication. So let's just do one more verification here. Was it 102400? And let's use our random vector v just because it's a nice easy one. Okay, somebody give me a random scalar.
6.
C equals 6. Okay. So I need to show that if I multiply my matrix A, 1, 0, 2, 4, 0, 0, times my scalar times my vector. If I multiply that vector by the scalar, I get 6, 6, 6. Is that equal to the same thing as if I do my scalar 6 and multiply the result of 1, 0, 2, 4, 0, 0 times 1, 1, 1? Yeah, it should come out the same. So if I just put a weight of 6 on each of these columns, I'm going to have 6 times 1, 0 plus 6 times 2, 4 plus 6 times 0, 0. So in this case, I get 6 plus 12 is 18 and 24. Okay, does that equal 6 times the result, right? I'm going to do, it should be a big parenthesis. I don't want it to look like a matrix, just a big parenthesis. 1 times 1, 0 plus 1 times 2, 4 plus 1 times 0, 0. So this inside the parentheses, I'm going to have 6 times. I'll do that all in one step. So I have 1 plus 2 is 3. 0 plus 4 is 4. And 6 times the vector 3, 4 is 18, 24. Okay. So that's what it means to be a linear transformation. It means that it preserves addition and it preserves multiplication. Okay, so what is the domain of T here? What kind of x's can I multiply A by? What size vector?
3 by
Yes, so yeah, you already had told me up here that it had to have 3 entries to be able to multiply by A. So that is the domain. Those are the kinds of vectors that you can put in here. They have to be 3 by 1s, or you can't do anything. So my domain is R3. Those are the kinds of vectors I can plug in. What kinds of vectors do I get out? That's called the codomain. Go back to our example. What kinds of vectors did I get out when I did a multiplication of A times a vector in R3? I got vectors with 2 entries as results. So R2 is my codomain. All right, so if I want to find the image of the vector 1, 1, 0 under the mapping, that just means plug 1, 1, 0 into the formula A times X, right? So I'm just going to multiply A, 1, 0, 2, 4, 0, 0, times 1, 1, 0. Each of the entries in that vector becomes a weight on one of the columns. So I have 1 times 1, 0, plus 1 times 2, 4, plus 0 times 0, 0. So I get 3, 4. So we say that the image of 1, 1, 0 under the mapping T is 3, 4. Are there any other vectors in R3 that would give me 3, 4 as an image? Yeah, how'd you figure that out? 1, 1 anything will give you 3, 4 as a image. Yeah, because this third column sort of doesn't matter, right? No matter what weight I put on it, right? I could put a 7 there and it would still give me zeros to add on, right? Because my 2 entries are both 0. You could write that as, that would be fine. You could write that as 1, 1, A, or 1, 1 star. Yeah. Okay, now I'd like to find a vector whose image under T is 1, 1. So I would need to find, I want to find a 3-entry vector. Then when I multiply by A, I get 1, 1. So let me just write out an equation that says what I'm looking for here. So A is 1, 0, 2, 4, 0, 0. I'm looking for a vector in R3. We'll call it x1, x2, x3. So when I multiply by that vector, I get 1, 1. How do you solve that equation? That's what the solution looks like. How do you get it, though?
row reduce.
Yes.
Well, actually, technically, there's only one stuff. You have to scale it by 1/4.
Yeah, so like in 2 steps, you could row reduce this. Yeah. So we would row reduce, even though it's only 2 steps. I'm going to put it in the calculator to review how to do that. So we go to the matrix menu and oops, can't see. Go to edit. And what matrix am I row reducing? What are its dimensions going to be? 2 by 4. Yeah, because I'm going to take this 1, 1 and tack it on there. Okay, so I'm going to have a 2 rows, 4 columns matrix. 1, 2, 0, 1. 0, 4, 0, 1. And then I quit, go back into my matrix menu, choose math, RREF, matrix A. All right, so this is my row reduced echelon form. Oops. Oops. Say that again, Alex? No, there is not always a solution. That's a good question. Yes, there are sometimes going to be vectors that are the image of nothing. Like there's nothing that can get you there. Yeah, you would just say there is no vector whose image under T is 1, 1. Right. In the matrix, you would get something inconsistent. Yep. Yep. So this says that, what does that say? What does x1 have to be? 0.5, yep. So this says that x1 is 0.5. And it says x2 is 1/4. What about x3? I need an x1, x2, and x3. It's free, yeah. x3 is free. So my vector whose image under T is going to be 1/4, whose image under T is 1, 1, is 1/4, oops, sorry, 1/2, 1/4, free. 1/2, 1/4, anything. It's just a star, yeah. No. It could also be an A or, yeah, or x3, right? We've been using x3 usually. For a variable that's free, we just leave it its own name, yeah. And yeah, you could just pick a number, because I only asked for one vector, a vector, so you can put any number you want there. Okay, is 8, 12 in the range of T? It's almost the same question as F, right? I'm asking, is 8, 12 a possible output?
Yeah, absolutely.
Yeah, how do you know?
Because it's just a way to
Oh, look at that. You didn't even have to set up the row reduced, the augmented matrix and row reduce it. You just said, oh, definitely, I could put a 0 weight on the first column. 8, 12 is a multiple of 2, 4. It would be times, oh, no, it's not. Sorry. Sorry, what are my weights? 2 weight on the first column, a 3 weight on the second column, and then any weight I want on the third column because it's just zeros anyway. Yeah, so that gives me 2 plus 6, which gives me the 8, and then 0 plus 12 gives me the 12. Yeah. So yes, it is definitely in the range because I can get it as an output. If it's not that easy, you do it the same way we did F. You would do an augmented matrix, row reduce, solve. Either way, you can use the augmented matrix, yeah. Yeah, I mean, I would not have seen right off the bat that what weights to put on those. Somebody was quick. I would have set it up and solved it. Okay, so what's the range of T? So the codomain is R2, right? Because I'm always getting vectors in R2 as my outputs. The question is, can I get every single vector in R2 as an output? You have a free variable, so yes. Yeah, I've asked you this question before, just in a different way, right? If you can get every possible B as a solution to AX equals B, we said that the columns of the matrix what R2? Span, yeah. So this is all an alternative way of asking this is, do the columns of A span R2, right? Okay. And then, so what do you have to look for to see if you have, if the columns span a space? A pivot in every row. And I've already done the row reducing, right? I did it up here. I have a pivot in row 1 and a pivot in row 2, pivot in every row. So the answer is it spans R2, which means that the range of T is all of R2. I can get everything in R2 as an output. Yes, a free variable is the same as having a pivot in every row. Yep. Pivot in every row implies that the range is all of R2. I can get any vector in R2 as an image of something under the mapping T. All right, so for the activities, I'm going to have you start with super basic algebra. Like, this is not a matrix transformation. This is just the line that you would have learned how to graph, 2 years ago. T of x equals 7x, right? And I'm going to have you work with the definition of linear transformation with just a transformation that goes from R to R. So your inputs are just regular real numbers and your outputs are just regular real numbers. So you're going to work with that a little bit before you jump in with matrices.